project is really to try to improve the conversion efficiency of sunlight in a photovoltaic. And we do that by taking the electrons produced by the high energy photons and converting them to additional electrons inside of the device. The fundamentals of the idea have been around for a long time, and all the physics is more or less known. There are some nuances that we need to figure out. But so I would say in some sense that it's not a high-risk project because the physics is all known. On the other hand, the device structures and the materials combinations are sometimes a little tricky, and it hasn't been done yet, so we don't really know exactly what to use. So one of the nicer aspects of this project and this idea is that it actually starts with materials which are known to be good photovoltaics. So silicon, crystalline and thin film silicon would be good candidates to start with. We have ideas for several different existing photovoltaics, and you start with those, and the idea is actually just an amplification technique. So it's a way of improving the performance of an existing material. We think that's really an advantage because we know where to start. This is a sort of an advanced concept that is using existing materials and making some fairly subtle modifications on them to try to get a better conversion efficiency in the photovoltaic.
Well, this is a project that actually is going to require the expertise of lots of different kinds of people, from people that will actually be making the materials or modifying the materials to see if we can get these structures that improve efficiency, people that are going to look at the basic mathematics, the basic mathematical modeling, to understand how current, maybe enhanced current generation may be collected in these materials. It's going to involve people that can understand the processes that go on at semiconductor interfaces. So when a photocarrier moves from one material into another, is it likely to give us this extra current, or is it likely to actually be combined at that interface, which often happens in interfaces if they're not designed correctly. And so we have to be able to understand fast transfer processes. We have to be able to understand whether we're creating additional defects by putting these materials together in the way we are. And so there's fundamental measurements that have to go on, fundamental design ideas that have to be developed, and also new types of material synthesis that are involved. So we're trying to bring together people from several institutions, most notably the University of Oregon and Oregon State, but we have also one collaborator that will be at the University of Illinois who has a lot of materials expertise. In trying to develop proposals, to get external funding and to get people interested, one has to usually, or it certainly helps a great deal if one can establish proof of principle. And we felt that a key piece of equipment would be one where we could basically screen many samples in a short time. So we had to have some quick way of screening these materials as they're being synthesized. So BEST was very instrumental in helping us go that first step, that is to acquire a piece of equipment that will be used in that screening process.